Yeah, okay. So why is inverse kinematics not enough? We have a way, and you're gonna see that we don't have to do this by guessing. We can actually have optimization methods that we can use to take one initial configuration, one goal configuration, one initial configuration and a desired state in the workspace and figure out what is the configuration that will achieve that. Why is this not enough? Why do we still have an hour and a half to go and things to cover before we can talk about before we can talk about motion planning and then integrated testing and motion planning? So why is inverse kinematic not sufficient for our goal of getting the robot to move efficiently in the space? Yeah, we might have collisions, and we want the robot to avoid colliding with other objects and with itself. So we need to take that into account. And one thing to note, and this is a slide I added after hearing the talks yesterday. I think this conference is about bridging the gap between the symbolic and the continuous, but specifically here between the discrete and continuous spaces where we want where we use high-level actions that typically specify the desired state or the desired configuration, but robot actuators exert force that is proportional to the difference between the current configuration and target configuration. So the motion is continuous. We need controllers that actually monitor the progress. And as I said, this tutorial does not focus on the control aspect, which is a whole different notion and very, the domain that has its own complexities. But I think that we need to understand these control mechanisms in order to do effective task and motion planning. Now, if you look at the code that basically takes the result of the inverse kinematic solution, you will see that in order to actually get the robot to move from its current configuration to a target configuration that is prescribed by the inverse kinematics, we'll have to apply this over time. So there is this continuous loop that goes on until the desired configuration is achieved with some tolerance. So when we ask what is not captured by inverse kinematics and control, we actually move on to understand that even if we figure out how to move the robot and the fact that, or what are the possible movements, and the fact that we need to take this continuous motion into account, that is still not the whole story, because we need to understand how the robot interacts with its environment and avoid collisions. So there are various approaches to motion planning, not something that we can cover effectively in the time that we have. I'll just mention that there are optimization-based approaches to motion planning that actually capture the space and try to optimize the movement within the space. But more commonly these days, people have been using sampling-based approaches, since they capture or they allow us to use generative models for sampling the space and understanding the connection between these samples. And this is often easier to do in complex settings. So it really depends on the dimension of your space, the choice of the solution approach. Anybody familiar with these two approaches? Yeah, which one do you use?
Well, I mean, I took one class in robotics and we talked about this when we were talking about motion planning. I remember it being called RRT, but the demo that we were showing looked more like the one, the image on the right. So not quite sure what the difference is.
Okay, so the two approaches that we see here and the planner that is used in the notebook is actually an RRT star approach, so an extension of the RRT. So both approaches are based on sampling. In a probabilistic roadmap, you sample through well, not necessarily uniformly, but you sample across the state space and you try to connect the adjacent. So you sample, so you have an initial configuration, and then you sample from your space. You find out whether, or you remove from this set the points that are in collision. So sometimes very obvious, but sometimes very complicated to figure out. But assuming that you have this function, then you filter out the points that are in collision. And then you connect, and this is the complicated part, you try to connect configurations to their neighbors, to their closest neighbors by creating these paths, assuming that when they're close enough and you sample the path between them and you find no collisions, assuming that if they're close enough, you have a way to compute control motion that will get you from one configuration to the other. Then you have a graph. And the thing about the probabilistic roadmap is that it's a multi-query graph. So you can use it multiple times for different initial positions and goal positions. And then you just use A star, like what we used for task planning to solve this task. In a rapidly exploring random tree approach, you start from an initial configuration and you expand from there. You don't randomly sample through the space, but you actually just extend your tree gradually, where in the basic approach, you don't correct yourself, but in a RRT star approach, you actually apply corrections. The motion planner that is used in the tutorial is an RRT star based approach with a motion planner called CLAMPed. This was the hardest part to get into the notebooks. So Yuval and Guy, my students, did an amazing job here. So now I encourage you to try to complete task number 4, but I do recommend looking at the things that happened between, or what we write about when we discuss. So the transition from forward and inverse kinematics. I just want to point out that as opposed to what we tried to do before, where we were trying to do inverse kinematics ourselves and try to guess, here you are going to use an off-the-shelf inverse kinematics solver. And there is a really nice example of a setting where there is no inverse kinematic solution. So this is on the way to the task, but I encourage you to have a look. And then let's take maybe 10 minutes to try and complete task 4 with this motion planner, which is called CLAMPed. So interestingly, even though my computer is connected to electricity, so that's the reason. If you're joining us, we're doing an interactive tutorial. So if you want to, I'll put up the barcode for we're now doing a tutorial 2. Yeah. Well, yeah, did you get it? About the inverse kinematics, it's lab 3. Yeah. Lab 2. Lab 2. Yeah, sorry, lab 2. So now we have this agent that is trying to move blocks around. Things are getting more and more complicated. Did you guys manage to run the planner? Did So let me go over this just briefly while you guys are working. So what we end here with a setting where we have a position, we have a configuration that achieves the workspace condition, but there is no way to achieve the inverse kinematic is unsolvable because the robot collides with itself. So if the robot ignores the obstacles in the environment or its own position, and it might fail to find a solution. And of course, more generally, if you ignore the constraints, you are bound to fail. And that's how we motivated motion planning. So again, what we see here is a motion planner. And where the robot is modeled, the environment needs to be modeled very effectively. And this is one of the obstacles in creating good simulations. You need to know the environment. It needs to be modeled. Sorry, my mouse is not allowing me to rotate it in a reasonable way. The thing that I'd like to point out here is that there is some maintenance of the fact that there is some notion of block 1. This is information that is coming from our simulator, and of course is not available when we actually deploy a robot, but for now this is sufficient. So in the environment. We model the different objects. We take these, for example, here the blocks, they're positioned on the table. This allows us to compute plans that take them into account. What happens when a robot picks up an object? How do we avoid, what happens to the space if the robot now picks up an object? What happens to that, to our, yeah.
We no longer have to care about collisions between the robot and that block now.
Right, but
The robot's larger.
yeah. So what is common is to, when a robot picks up an object, we commonly change the robot. And now the robot is the robot plus the object. And we need to take that into account when we do our plan. It's a different space because often that means that the robot is larger and we have to take a larger bounds. So updating the space here, we see examples of how we update the space. And this is an example of how we attach the box to the end effector and now change the effective configuration of the robot. And we can see here that the robot is depicted as a robot plus the block. And that's something that we need to maintain. So what I hope you saw now in the example is you had the chance to see RRT star in action. And I'd like to point out this part of the code. So your start configuration is something like above yellow block config. Where does this come from? What does that mean? So we have a motion planner that is supposed to plan from configuration to a pose, and the start configuration is above yellow block config. What does that mean?
End effector motion of the end.
Yeah, but where do you get this from? Where does this information come from? How do you know what does it mean to be above the yellow block? I mean, it's a thought-provoking question. It's not supposed to have a specific answer. I just want us to note that this is a violation, in a way, a violation of or this is a way in which we hard code these kind of capabilities often in robotics, and you will see a lot of skills and a lot of situations like this where above yellow block config will maybe indicate a certain length, a certain height above a specific object. And this is the fragile, these are the points where we have blinking on the word, we have failures might occur because these are hard-coded kind of capability, hard-coded notions that might cause our planners to fail. But hopefully you managed to run the motion planner on a path that it computed here. So here it was supposed to get from one configuration to the other. Remember in your mind all the time that there is some translation from these abstract notions of objects here to configurations. And this translation is what we're going to discuss next. And hopefully you managed to run your solution efficiently with a motion planner. Now let's look at what happens now when we identify a path. Basically, you try to move the object and you try to execute your plan. So did you guys manage to run the planner? Did that work? Great. So let's look at the execution loop for a complete planning and execution loop. Here, the task is to move several blocks. So you start by picking up the yellow block from the right table. You move above the block. Some notion of block is being maintained here by block 2. Then you drop at the target position. Then you pick up the purple block, you put it down. I'm gonna run the video again just so we see that this is a multi-step plan that is being executed. And everything is going perfectly well. The robot manages to figure out exactly where to put the object, where to pick them up from, where to place them. All good, but actually not really. A lot of things might fail. And we need to take into account the fact that in many robotic settings, this is something you need to really pay attention to. In many robotic application, many robotic frameworks, you will see these skills as hard-coded without any ability to recover from failure. Okay, so these are hard-coded without monitoring execution, without maintaining state estimation. They are typically bound to fail. So what is not captured by motion planning? Both the aspects of the task planning procedures that capture the high-level task and what needs to be achieved, and also not the control aspects of how motion actually is executed and monitored. Motion planning is just about figuring out how to compute a path that gets us from an initial configuration to a goal configuration without colliding with obstacles. Now, task planners operate in symbolic space, but real-world action, as we saw, require a continuous activation. For example, the placing of the block, we actually need to take into account the execution of the action and the continuous space in which they operate. And creating these functions is very hard. Anybody try to create this generic pick and place function? It's a very challenging task, taking into account all the possibilities. As I said, you typically see a lot of hard-coded skills in these settings, which I think is a major issue that needs to be addressed. So now let's get to the core of what we've been building here. So we had task planners that worked in the symbolic space, and the task planners' capabilities are expressed by the fact that they can reason over very large sets of states. They can manipulate partial descriptions of the environment, etc. While the geometric planners operate on a very specific and detailed representation of the world. For example, a task planner, this is an example by Leslie Keibling, which she works a lot on task and motion planning and does very interesting work in this realm. So a task planner basically can decide that the living room needs to be traversed, or in our running example, that an apple should be picked up if a person is hungry. But typically in the task description, you disregard the detailed arrangement of the space, here the detailed arrangement of the furniture. And in contrast, the motion planners deal with the geometry. They know how to move in the physical space. They know how not to collide with obstacles, but they don't have this notion of a task and why operations are performed. So when you combine the two, if you combine task and motion planning, you basically inherit the challenges of both problems. On the task planning side, you have very high dimensional spaces and long horizons. You have the need to capture very complex situations. And then in the geometric side, you have to take into account the specific capabilities of the robot, reachability constraint, joint limits, collisions, etc. Becomes very complicated very quickly. So a traditional approach to solving task and motion planning was the decoupled approach. You first solve the discrete planning problem, then you perform what is called downward refinement. So you just translate the actions into motions in the continuous space, and you assume basically, you operate under the assumption that downward refinement is possible. So for every correct discrete plan, you can find a correct continuous plan. This is, of course, a very fragile, brittle approach, which will fail many of the times, just because the information that we can capture in continuous space, in the discrete representation might be limited. What I would like to talk about is the way in which we can integrate the discrete planning and the continuous planning tasks. So what would be a challenge that you guys can think about, given what we've seen so far in the combination between discrete planning and continuous planning? What would be a challenge, kind of a first challenge that we would need to address? This is Shaky, just to give you a motivating example. This is one of the first robots that was designed to do task and motion planning. This is actually the robot that motivated the creation of PDDL, which is the language that we saw, which is a form of strips, the planning language, and also the creation of A-Star. It's actually a really interesting story because Shaky was developed in SRI, and I was told that there was this corridor where there were various researchers. So on the one end, you had the people that were working on Shaky, and they established the task planning community, which deals with very abstract representations. But at the other end of the corridor, you had the behavioral robotics, reactive robotics community, which developed swarm robotics and Roomba, and so really we can see very different paradigm, different thought processes that created two very different communities. But what would be a challenge here? What is something that we would kind of need to address when we want to combine this ability of Shaky to move from one room to another, pick up stuff, and actually translate that into continuous motions? Or otherwise put, can't we simply do task then motion planning? And I hope that with the exercises that we've done today so far, I hope you realize that the answer is no, but I'd like us to discuss specific challenges that we would want to address. So this is a depiction of one of these challenges, right? We want, the person is telling the robot to pick up a block, but the robot has no notion of a block. So the first challenge that we will address is state estimation. How do we represent the environment in a way that allows this interaction between the layers? And again, we have these three different layers of abstraction that we want to combine. The lab that we're going to do now is the actual integration of task and motion planning. This is lab 3. If you want to join, I'll put up the website just in a minute. I'll just first explain. I mean, this is the long link. But what we're going to do now is we're going to try to create and implement the state estimator that converts the observations of the physical world into state representation that can be used by the planner. So this is the cheat. If you get this from the simulator, this is privileged information that you're not supposed to rely on when you actually want to plan for robots. But here we're gonna have some cheats because it is a simulation and we want some of the aspects. We want to focus on some of the aspects, but as you can see here, some of the features in the environment are going to be provided. And you will see some of these, for example, these kind of these violations of real world kind of assumptions in these kinds of settings. So we're going to have a table that tells us when we see an object, which object it is. That's something that usually you will have to monitor. It's just state estimation, continuous state estimation is a very complicated issue. So we won't address it here, but I do want to pay attention to this notion. So the question that we're going to ask ourselves in the next assignment is, how can we determine whether a block is on a table or on another block? If we don't have access to the scene, we can't label it. We rely on the autonomous agent to do this on its own. And yeah, okay, it might have a vision component and allowing it to know where blocks are. Still, that doesn't solve our problem. How do we know that the block is on a table? How can we know this from the environment, from sensory information that is received from the environment? So we have these setting ideas. What does it mean for a block to be on a table? How can we capture this?
And we do some kind of depth estimation.
We can do that. So if we have a depth camera, we can do some depth estimation. That's probably would be the way to go if we didn't have, yeah.
Every object in the scene has to be on something, so you can go through all the objects that you can recognize and look beneath it and determine what the object is that's beneath it.
Okay. Yeah, typically you don't want to do this for all objects because you might get exponential blow up, but maybe some optimized version of what you just described. Okay, so in the assignment or the task that we're going to solve now, this is the cheat. This is the privileged information that we're going to have access to through forces that are applied on an object. Of course, also in reality, you might have these kinds of sensors. Here, we're just going to assume that the simulator is giving us the normal forces that are active active when the block is on the table, and we're gonna use those to populate our state estimation. So to understand whether an entity is on entity, we're gonna use that. So we're gonna implement these predicates that we saw in the task planning task where we had the block on block A on B. We're going to actually implement it using the forces that are provided by the simulator. And for that, so for that, I'd like you to do task 2 in lab 3. So defining these predicates, right? This population of the predicates and they're part of the state estimation. And if you just joined, this is the link to keep, I should have had it somewhere, maybe on all the slides. This is, if you want to join, this is the barcode for joining the tutorials. We're now doing lab 3. Lab 2 or lab 3, task 2. Yeah. let's take 10 minutes to see if you guys can figure out this challenge. And if just realized that I forgot to run mine, so I'm gonna run it now, which is a good way to remind you, if you wanna run these. They're easily runnable from the Git repo, but note that you have to change the runtime configuration. You have to make sure that you're running on a GPU because of all the rendering that's occurring here. So let's take 3 more minutes and then we'll discuss what this means and whether this is an effective approach to state estimation. So what is how did you guys implement you guys finish? Wait a little longer or okay? Continuing? How did you implement on block A, block B, given the current state?
I just mapped each of them to their GIF IDs and then used the on entity function.
Great. So given these two blocks, you could extract the information from the simulator and understand whether they are each other. Same from table, right? What is the difference here if we're trying to implement, oh, sorry, where is the next one? On table, yeah. Yeah. Sorry, did you try also implementing the next functions where we needed to check the, yeah, sorry, I'm missing out on something here. There was another one, or maybe I removed by mistake. So yeah, so thank you for the answer. One thing to kind of note, and I hope you got to these points, what is the state here? What's going on here? What is supposed to be the value of on block table? False? Holding? But it's actually it's not table, but it's also holding.
The gripper is still connected to it.
What?
The gripper is still connected to it. So technically it's holding it.
No, it's technically both holding and on table, right? In a continuous space, there is this moment where both predicates are true, even though our PDDL definition disallowed that, right? We said that the precondition is that the gripper is empty for it to be picking up the object, and the delete effect is that when you picked up the object is no longer unstable and the gripper is no longer empty. But here we have this moment where both predicates are still true, or well, not necessarily that the hand is empty, but definitely not that the block is still on the table and being held by the gripper. So this is a state that violates our test planner condition. The thing to note here is that we need to monitor the state and actually have an understanding that this is about to change, or something that actually monitors or that captures these states that conflict with our task definition. Okay, so so hopefully you've successfully implemented on table and on. And what I want us to note is that in order to extract this information for the current state, we, unless we have a different way to, or we optimizing in some way, we would have to check all the predicates at any given state. This is very expensive to perform. What could be an alternative? Here you see what we do is in order to estimate the current state, we go over all the blocks and check whether they're being held by the robot, whether they're on the table and whether they're on a different block. This is computation that is super inefficient. What could you do instead? So a common approach to actually making doing this test more efficiently is to maintain some Bayesian filter that takes the information about the class state, the action that was performed, and tries to focus attention on the predicates that might have changed. Otherwise, this is a very daunting task. This is the other one that sorry, this is what I meant. There'll be other predicates that we can implement using these implementations. It's clear and empty. The problem here is, in order for us, what is the difference between on table or block on block, is that here we would have to check all the blocks. Again, these are very expensive. So state estimation is something that can cost quite a lot. Here you have an extension of this idea to a setting where you are not necessarily given the objects, but you want to capture the state information using, for example, a camera. So this would be an RGB camera that you can you could use if you did not have access to privileged information. I didn't include this in the tutorial, but I think it's really nice to see how you could actually interpret the scene using the information that is incoming from the camera. So the state estimator function basically would need, and again, this is not a good implementation. You would need to do this in some informed way. You process the information, you get the states, and then we have some process that gives us the state estimation for our task. And again, this is not the end of our challenge, because when we want to plan, we want to be able to understand what are the relevant states for our planner, for the task that we want to achieve. And this is where we call this sampling, but any learning-based approach where you have a way to generate a generative model for generating the states that you want to consider. This is important. So what's going on here? What is the challenge that we're trying to address? We have on the top, the current world state is that we have 3 blocks on the table, and block B1 is being held by the robots. What is the task that we're trying to achieve? What is the desired task? Right, so the current task is that we have on table B2, B3, B4, these are the clear blocks, and this is the block that is being held. And the plan that we generated using what we did for the task planner is exposing the desired PDDL state. So what is the difference? Let's just make sure that we understand what is the desired state. What is the thing we're trying to achieve?
Place it on the table and not any other block.
What?
Place it on the table and not any other block.
Yeah, I place it on the table, but I can't hear the
Not
second.
any other block.
Okay, and then and a clear spot on the table. So how do we find the right spot on the table? Now we have our motion planner. So we know, once we know the configuration, we'll be able to compute it. But how do we find it? We only know the current states. How do we find a place, a position on which to place the object? This is no longer easy to say on table. To reach this point where we're on table, now we actually have to find a free space. How do we do this?
Potential,
Sorry?
use a potential where there are objects, there is a, if, where there is a, like, automatically will come up to a positive at that place.
I don't know this method. Can you explain more?
So you would say that you know where the blocks are from your perception system.
Perception. Okay, yeah,
So
okay,
now you would say that there is a negative on those,
okay,
just some Gaussian.
yeah.
So the place with the least negative is.
Oh, I see. So from each center of so this would be trying to compute area which is vacant because or you would have kind of the propagation of the locations and you, how would you find it still? You would still need to sample from the environment, right? And check whether what is the okay, so great. So what you just described is a way to sample the space. Still, we would have to have multiple configurations to consider. And then after we sample from them, we need to apply the same reasoning that we did in the first part of this tutorial where we're saying, okay, does this comply with the requirement? And the second part of the tutorial where we're saying, now that we want to examine this, we need to figure out whether there is a plan that in the motion planning space, configuration space would be, the robot would be able to achieve that position. So these are all, and this is the important part, these are all the same state in the task space. In the abstract space, these are all on table B2, B3, B4, and B1. But they're very, very different in the from the point of view of the robot and from the configuration space view. So the question that we now ask is, okay, so we did all this, and the question is whether we are done. And I'd like us to complete the exercise, so the question, sorry, the task that that is kind of the last task of the tutorial, and talk about. So I'll take a few minutes to kind of finish up, and then we can talk about task and motion planning research and kind of how we can address it. So yeah, so basically, in the interest of time, I recommend just reading through, seeing that the solution makes sense to you. So now we have, as I said, we do have our state estimator. We now want to translate that into kind of actions that we can perform. Okay, so here we have a state estimator, and now we want to translate that into a plan. And we discussed this notion of sampling and the need to sample. How do we translate that into decisions that we make about the space and the task? And then we'll end the tutorial with a discussion about various approaches to task and motion planning and the challenges. again, just to focus our attention, I'd like us to think about how we would perform the put down action, following up on our discussion, assuming that we have a way to sample positions. How would we be able to extract a valid plan for the desired state that we want to achieve? So what is the challenge with sampling? What was kind of the key challenge that we need to address when we talk about simply sampling from the space? What might happen?
So we need to make sure we're sampling only from relevant states, because otherwise there's a probability of 0 that we'd end up with a state that's actually on the table.
So, and how do you go about such a?
I guess you need to create a distribution for the table. Like anytime you want to sample from something, you have to have like a distribution order where the support is only to purchase or
What is the problem with the samples that we collected here, for example?
Like the one on the right hand side, like the top right hand, technically you can place B1 there, but your arm probably will collide there.
Okay, so great, this will collide.
Yeah.
Another problem with the sampling set that we generated here?
Bottom left, it's too much on the edge, it might fall off.
This is too much on the end, very risky, something that we want to take into account. Another thing that's problematic with the sample set here?
Oh. The one on the top left, the blocks have been moved around.
Yeah, so it's the same symbolic state,
Oh,
but now we have to do all this work to actually achieve this. We don't want that. So we have to maintain the notion of, I mean, we have to understand, we have to kind of make sure that when we sample in a way that doesn't require us to actually work in order to get to that state. It would easily be replaced. So here, what we actually do is we try to combine these, all these components that we've discussed. Hopefully, kind of figuring out that, you know, sample on table is also each of these components needs to be considered. We need to think about how to implement that in an effective way. Of course, when we don't have the sensors that provide all these privileged information, that it becomes even more problematic. Whether objects are colliding with each other is hard to do if you're doing a vision-based approach, for example. These are, I hope you had a chance to have a look at all these functions and how they're implemented. So sampling a free spot on the table for a block is something that is by definition going to cost us a lot. So when we have to generate blindly these configurations, we're going to spend a lot of energy redundantly. So the last thing that we're going to look at before we start to kind of wrap up is task 5, where we want to implement skills. And this is kind of the core, in addition to state estimation, which is already very challenging. Now, oh, sorry, I have to present, sorry. I try to juggle between them. So the last thing that I would like us to kind of to discuss is how do we take all this, the state estimation idea and the sampling based approach that we kind of discussed right now in order to perform desired action to achieve desired states. Now we're going to talk about the skill executor. So this is a key component in task and motion planning, creating skills in a way that allows us to reuse them for different tasks. Of course, we don't want to be able to pick up a specific block in a specific configuration. We want to be able to create these general purpose skills. And the idea with skills is that they typically allow us to reuse them. We can create this general skill and reuse them for different tasks. So the final task that I'd like us to try is task number 5, where assuming that we've implemented the motion executor and we have the sampler, how do we implement these skills, this pickup skill? How do we, for example, or here we have pickup, how do we implement put down, unstack, whatever you guys want to attempt? As I said, the solution is down below, but how all this combines into actual execution of an action in this combined space, so task and motion planning space. Let's take, in the sake of time, let's take 7 minutes. So at 12:15, we'll kind of start wrapping up. But I think this is the core, right? Getting to a point where you can actually implement actions and not just discuss the states that you want to achieve, but the how. How do we actually use everything that we discussed today to actually achieve and be able to actually perform an action? And remember, these were coded very in a very abstract way. These are the same actions that we had in our scripture presentation when we talked about how does that translate into actual motion? So let's have a look. Is that okay? Or should I wait a few more minutes? I'll wait 2 more minutes and then we'll start wrapping up. So let's look at kind of what we've been working towards. We started the day with discussing this abstract symbolic space representation of, for example, the notion of pickup. The preconditions for pickup were that gripper was empty, the block that is being picked up and is supposed to be clear. The effects, the ad effects of this operation were that now the block is in hand and that the gripper is only, and the big effect is that the block was no longer clear, no longer on the table, the gripper is no longer empty. And now all this is translated to operations that actually need to be applied. So you get the block identifier. And this is again something that you should be able to get from a state estimator and not from the information that is maintained in the simulator. Then you want to move the end effector above the block. We did that using motion planning. We want to execute this, and here note that there is no monitoring. We also have to monitor the execution. Then when you get to the position from which you can grasp the object, you basically just close the gripper and pick up the object. A lot of assumptions that are going into that are being applied here, a lot of relaxation or assumptions, unrealistic assumptions that are made here, but just to kind of demonstrate the idea of this integrated task and motion planning approach. We don't have time to kind of cover everything, but I really encourage you to look into the tutorials, the notebooks. There is also a fourth one. I'll just show it here. We won't have time to do it, but you can use these same ideas to solve more complicated approaches or challenging problems. And then just to show you the fourth lab, which is about trying to actually perform all this when we combine task and motion planning. So how do we combine these approaches? How do we propagate information to the task planning about the motion plan? How do we take the constraints into account, for example, in our sampling procedure? So this is kind of, a more complicated kind of approach or more elaborate approach. So hopefully, throughout this tutorial, I managed to convince you that the task of bridging the gap between the physical world and the representation and it's kind of the information that we extract from the simulators, even if we have these strong components that provide state estimation, very strong state estimation capabilities and allow us to account for the different constraints that are in the environment, still we need to account for the different layers of abstraction. We need to be able to represent the environment in an effective way, understanding what are the important predicates that need to be maintained. And hopefully I managed to convince you throughout this tutorial that actually maintaining them is a challenging task. Understanding how to figure out and maintain or understand whether or to fuse all these sources of information to kind of a unified state estimation component is not a trivial task. A lot of the tools that we have today off the shelf allow us to extract a lot of this information that used to be very hard to encode. So usually in the past, we had to encode these kinds of information, that the fact that Apple is food and picking up that the Apple would comply with the user's requirement was something that we needed to encode. Today we can use, I think that's one of the key components, the key capabilities that we can, that the foundation models provide these days, LLMs, etc. Understanding this world knowledge is something very extremely beneficial to these kinds of tasks. So we started today by considering task planning, experiencing the difficulties of generating these strong general purpose solvers that allow us to find a sequence of high-level actions that take us from an initial state to a state that satisfies the goal condition. And I hope that I convinced you that when you start to work on robotics and real-world problems, just understanding, populating the feature space and understanding what the current state is becomes a very challenging problem. Accounting for uncertainty of the sensor function, again, a very challenging set, and something that we need to address. It's enough to have a different kind of lighting, or for it to be day or night, for all the things that you've learned to be completely useless, because the observation become very different. Then we discussed motion planning, and we experienced, I hope you enjoyed this, the part where we try to figure out the complexities that go into actually understanding how to move the robot. Now, once it decided that this was the apple it wanted to pick, how do we represent the environment as an obstacle, or how do you represent all the objects as obstacles? How do you play effectively in this space? So we saw inverse kinematics. We understood that is a very hard optimization. It's already a hard optimization problem, trying to figure out what configuration we want to achieve. But then we realized that that's not enough, because inverse kinematics cannot capture the obstacles in the environment. So we performed motion planning. We saw an RRT star-based planner, and managed to use it to solve the problem of picking up the block. So as a reminder, motion planning here, the definition is very, so this is where the bridge needs to be created for task planning. Here, even if we assume that simplistic, we use a simplifying assumption that we know the environment, finding a collision-free path in high-dimensional spaces is extremely difficult. And then there is still work to be done, because even after we find a path, we still need to find a way for robot to follow that path, given its capabilities, given its ability to monitor execution. And we do that. This is something that we did not cover, but is a very important to understand the capabilities and the uncertainty. So, a lot of these models rely on very accurate actuators, but that's an assumption that is not always relevant in the real world. And I think that a lot of work can be done in this realm, bridging these gaps and understanding these different scenarios. And of course, the question is, are we done? Is there anything to explore in this realm? And I think that the answer is yes. I think that there are a lot of open problems in robotics. And I think the more evolved the settings and the tasks that we want our robots to achieve, the more there are still open problems that haven't been resolved. So there are this field is an evolving field. It hasn't been around for that long. So these bridges that are created between these communities is something that I see increasing in recent years. And the approaches, and if we kind of look at the spectrum of purely discrete solutions, which fall under the realm of task planning, to purely continuous motion planning approaches, you can find a lot of approaches in between. This is, for example, multimodal motion planning. Just to give you an example, is the planning problem is an approach that solves the task and motion planning settings using motion planning. But here, when we attach, we basically define the different configurations of the robot. So we kind of understand what are the possibilities in terms of, for example, holding a block, putting it down, and then you can plan in that space for the different modalities. But I think the important frontier is actually this integration. integration. How do we combine all these challenges into one framework that can perform effectively? And I hope that I convinced you by experiencing what task planning is, what motion planning is, and a little bit talking about control, how, although these are complementary problems, and again, as I said, solved with very different tools, developed by very different communities, I think there are many opportunities for combining them. There is no possibility to talk about robotics these days without discussing the advancements that are made by foundation models. And there are amazing advancements. I keep discussing this with people from industry that have completely, that can solve what seems to be very complex problem without understanding anything about robotics, just learning and the capabilities, using all these tools. But then when we have this discussion thoroughly, at the end of the day, the fact that we don't understand the relationship between the task planner, the motion planner, and the controller makes these settings, these frameworks super fragile. They are not robust. You cannot change anything in the setup. If something works, then then you can't touch the setup, because if you move the lighting, everything falls apart, because when you do these things, we lose the understanding of why they work. One thing that I think is extremely it's a rising field, rapidly developing tool are the world models. I'm waiting to see how they're going to change the way we work. But so far, we've been using a lot of, at least in our lab, we were using VLMs for our state estimation, but we had a really hard time with the transition functions. We really, like the frontier that we kind of, I'm saying a hard time, but actually I enjoy the fact that it's still very challenging to understand what will happen when you try to pick up a ball. And now, we should wait and see, right? This is a field that is advancing so rapidly, then we'll have to see if these world models are going to make it easier for us to understand the effect of actions in the physical space. And also, this is something that is being extensively developed, these vision language action models. So how do you connect perception to actuation? But I still think that these are going to be limited for a very long time to very simple tasks. And to kind of end this presentation, I wanted to show you some examples of how I've been working on bridging the gap between these different realms. So this is an example of the work that I did in collaboration with Silvia Ferrari from Cornell and with John Schuschmidt, where we took this abstract idea of role recognition, which typically was developed by the task planning community, very abstract space. And so role recognition is about observing the behavior of an agent and trying to understand its objective. So, for example, where is it trying to go? In fact, the work that I did previous to this one was in the symbolic space. But here we adopted this idea to control. So these are, Sylvia is an expert in control theory, and we kind of fused this idea. We made it possible for us to analyze using some a Bayesian filter to understand the trajectory, to map the trajectory of the robot to the reference trajectory, so the optimal trajectory to the next waypoint, and trying to understand as soon as possible where an agent is heading. This is the work that I presented here, where we bridged the gap between perception and task planning and control. And the thing that we're showing here is that the foundation model is making a mistake. So the classification here is wrong. But by actually understanding this limitation and understanding the structure of the foundation model, we were able to create robust beliefs, so we could plan robustly in this space. And I do want to encourage you to explore this realm because I think that with all these amazing and rapid advances in AI technologies, I think physical AI systems will still be about combining skills, about developing these different components, understanding them. And I think that's a kind of fundamental field of capabilities that we need to create. One thing of particular interest or that is underexplored is this notion of uncertainty in perception. So a lot of these models are developed with this notion of deterministic kind of reasoning, and that really limits their applicability and their robustness. And I think we should develop techniques that take these limitations into account and propagate them into the decision-making process. So I hope that I convinced you that task and motion planning remains today one of the central challenges in building autonomous AI agents. Those that actually we want them to deploy them in the real world. And I think, and I believe that, especially in the context of this conference, I think that a lot of benefit can be achieved by combining the different abstractions and the symbolic reasoning, the geometric planning, and the learning together to create intelligent systems. Thank you so much for attending this tutorial. I had a great time. I hope you enjoyed the labs and the interactive format. It's a bit untraditional, but I think that for me, at least that's the only way for me to actually learn when I try to solve problems myself. So hands-on kind of approach. If you have any questions, please, we are really happy to engage about this content. We already have our Git repo, and that is it. Thank you so much. Enjoy lunch. Thank you.